Hi everyone, I'm Mei Hui from Beijing Institute of Technology. First of all, I'd like to thank the World DB Endowment and the World DB Endowment Award Selection Committee for giving me the Early Career Research Contribution Award. I'm truly honored and humbled to receive this award. Thank you. And for this talk, I'm going to talk about my recent work on cleaning, integration, and analysis for healthcare data. Before I present my works, let me spend a few minutes to express my gratitude to many people who have guided me and helped me in the past. Once again, I thank the award selection committee for the award, and I like to thank Benching for the nomination, and Divech, Jianpei, and Yuan Wang for writing the reference letters, and also my mentors, colleagues, friends, and students who have helped enrich my research career and made various contributions over the years. And particularly, I'd like to thank my PhD supervisor Benching and NUS professors who had advised me and giving me strong foundations in research and system development. I've also benefited a great deal from many established colleagues and academic senior siblings who have selflessly worked with me, guided me, and helped me in many ways. Thank you. And of course, my co-authors. Thank you all for the collaborations over the years. I'd like to thank my ex-colleagues at Singapore University of Technology and Design, and also my current colleagues at BIT for their support and collaborations. I'm also very thankful to the startup investors, the Singapore government agency SG Innovate, and China Xiaoshan government for supporting the 2 healthcare startups that I co-founded. And also I thank my medical colleagues in Singapore and China as well. Last but not least, I'd like to thank my ex and current research fellows, research assistants, and students for their trust and for working with me and many others who have helped to make a difference in my research career. And next, I will briefly touch on the 3 systems that form an end-to-end healthcare analytics pipeline, including DICE, COO, and FiberSharp. We have used healthcare as the main applications to drive the system design and implementation. I will also talk about an ongoing work which is on verifiable database, which is called SPEEDS. And DICE is a data integration and cleaning engine as a component of Gemini, which is our healthcare software stack. DICE ensures the data availability and quality by improving the healthcare data quality with machine-human data cleaning. It also rides on top of our Apache Singa, which is a distributed deep learning platform that we managed to graduate as an Apache top-level project last November. What we do in DICE is to make healthcare data more usable. It's well known that healthcare data is very complex in the sense that it has huge number of features and many concepts. Well, most current healthcare systems have like type complete or provide assistant for the clinicians to enter disease code. The older system, unfortunately, did not have such facility. And we do notice that different doctors often have very different writing styles, resulting in different textual descriptions of the same medical phenomenon. And here I show a real example from our data. We can see that all these text snippets in the left table actually refer to the same concept, which is the I63.50 in ICD-10 standard. But they appear to be very different from each other. And they are also significantly different from the canonical description of the concept in the standard. On the other hand, The medical standards change over time as well, and they will further introduce inconsistency and affect the data quality. Let's consider another real examples here. On the left-hand side table, we have concepts referring to the same disease with code K64.2 in ICD-10 standard. However, there are 7 different concepts in ICD-9 that can be interpreted or mapped into this concept. As a result, we find that in real-world database, inconsistent terms and expressions are very commonly used. So these 2 factors actually cause the healthcare usability problem. And healthcare data that have been collected over years tend to have noise problem. Therefore, the data cleaning and creation become a very important task in healthcare analytics. And to improve the healthcare data usability, we introduce a linker that is able to automatically link a medical record to a unified concept ontology so that the doctors can easily query the data based on the concept codes instead of the raw text or ambiguous keywords. We designed a framework that leverages neural networks to encode a concept into a numeric vector and then attempts to decode various text snippets. And the concept that most likely decodes the text snippet is linked to the corresponding medical record. We also collect feedbacks from domain experts and then use them to enrich the label data to improve the concept linking performance. And since we use the system to clean hospital data, the accuracy was verified by the clinicians. And we could manage to clean like about 90% of the data, and we rely on our cross-sourcing system, CDUS, to tap onto young clinicians and medical researchers to help clean the data that the machine cannot clean. And the second system is COO, which is an analytical processing system, which supports both OLAP queries and the cohort analysis query. The cohort analysis is a form of behavioral analysis that analyzes subgroups of patients or customers based on some common characteristics or their reactions with respect to certain events or actions. And in the healthcare system, we do medical cohort analysis for patients with similar illnesses and treatment plans. And in COO, we focus on both functionalities and performance. And for the performance, we implemented a novel storage layout optimized for fast query processing. It employs compression to reduce the space requirement so as to reduce the I/O cost. And we also designed efficient indexes for fast query processing. It supports both conventional OLAP queries and cohort queries with efficient primitive operators but with similar process flow. And COO is fully implemented in Java, and the demo and source code could be found in this URL. The COO system could be used to provide other forms of analysis, such as funnel analysis as well. And we have customized UIs for the medical cohort analysis, and we're working with the doctors to make COO as easy as possible to facilitate COVID-19 analysis, such as the comorbidity analysis. For example, we want to know what existing diseases cause more serious conditions for COVID-19. And also we can do medication analysis. And we hope it could be used for medical cohort analysis when the vaccine is at clinical trial stage. And next is Fabric Sharp, which is a variant of Hyperledger Fabric. We'll be trying to use blockchain as a decentralized system for personalized healthcare data management and analytics. And we've been optimizing blockchain system in terms of scalability and throughput. And in the new applications such as blockchain, collaborative analytics, and verifiable databases, we observe that they need the support of immutability and tamper-evident storage with forking or versioning capacity. So we designed the engine called Forkbase to manage multi-version data. And we also designed efficient indexes for reducing the data duplication and supporting the tamper evidence. And Forkbase has also been used to support provenance query processing in blockchain system. To support data provenance, we designed lineage chain, which captures the provenance during contract execution. And we also design indexes for supporting efficient provenance query processing. The source code based on February version 1.4 has been released, and we are now upgrading for February 2.2. I will cover these two systems with a little bit more details in the next two slides. And Forkbase is designed to support enriched data types and provide tamper evidence storage with efficient version management. We're still enhancing the system and extending it to provide efficient verification. As described in this diagram, a Forkbase cluster consists of four main components: the master, dispatcher, servlet, and chunk storage. And a servlet further contains three submodules for executing the request. And more detail about the systems and the results could be found in our VLDB 2018 paper. And with the lineage chain, we could enable a new class of blockchain applications whose execution logics depend on provenance information at runtime. To do that, we instrument blockchain runtime to record the read-write dependency of all the states used in any contract invocation, which is then passed to a user-defined method that specified which dependency to be persistent. And we store the provenance in the Merkle tree data structure, which is for the efficient verification. And to ensure the provenance query are efficient, we also design a novel skip list index optimized for provenance queries. And the experimental study shows that it's able to support provenance-dependent applications efficiently and incur small runtime overhead. And the last one is about our ongoing project Speeds. Nowadays, it's common for a business to involve multiple independent and distrustful parties. And since the parties are mutually distrustful, the underlying database must consider support for auditing, tamper evidence, and dispute resolution in its design. So there's a need for a new class of database system whose integrity can be verified. We've seen some recent works in past few years, and we've seen the emergence of commercial products and open source system. So naturally, with our existing work on blockchain, tamper evidence storage, and data provenance, we move into this area and design a verifiable database, which is called Speeds. And a verifiable database system needs to allow users to verify the integrity of both current and historical data. And we see the demand for VDB is on the rise, especially for sensitive applications and data management. And there are two requirements for VDB, namely the data immutability and query verifiability. And we identify four key challenges in designing the system, like we need a efficient and reliable storage management, and we need to provide efficient access method for querying immutable data, and we need to minimize the performance overhead of verification. And also, it is very challenging to support both verifiable OLTP and OLAP queries with good performance at the same time. So our space is an ongoing work, but we make use of various components of our existing systems. So we design a space to be immutable, transparent, verifiable, and scalable. And this figure shows the system architecture. It consists of two layers, the control layer and the storage layer. The control layer consists of multiple processor nodes that accept and process the request. And each node has three main components: the request handler, the auditor, and the transaction manager. And as mentioned earlier, we make use of the fork base. There are also multiple index structures built into the storage layer to support efficient verifiable query processing. And the implementation and optimization are ongoing. And our initial experimental study shows that the design provides good query performance and good throughput compared to emulated implementation of the baselines. So we hope to make space more efficient and scalable. Hopefully, we can report more of the space in near future. And with that, I'm ending my talk. Once again, I'd like to thank my friends, collaborators, colleagues, and students who have contributed and helped. Thank you for your attention. Thanks.